Hello everybody, my name is Alessia and I'm the lead lecturer here at Pearl Street Studio. Welcome to our introductory lecture on natural gas. So natural gas is one of the many energy resources that is used for generating electricity across the world. So the goal of this lecture is to help people understand what exactly natural gas is, how it's used to generate electricity, and discuss the considerations around using natural gas as an energy resource. So before I dive in, I did want to mention that this is lecture 3 in this unit. So this is part of a larger course called Introduction to the Electricity Industry. This is part of Unit 1, Generation and Storage. If you haven't already, we highly recommend that you go back and watch our lectures on coal and crude oil as energy resources, as this natural gas lecture is going to be referencing some of the material that we covered in those lectures. If you haven't watched those, we'll add a link in the notes to the YouTube video from our, to our previous lectures. But you can also visit our website at pearlstreetstudio.org to find them. All right, with that, let's dive in. So what is natural gas? Natural gas is a gaseous fossil fuel that is composed primarily of methane. So here you can see there are these little methane molecules, and the chemical formula for methane is CH4. Okay. Now, let's dive into how is natural gas created. So natural gas is a fossil fuel that forms through a process very similar to the formation of crude oil. And the natural gas used today originated from dead plants and microscopic marine organisms, such as plankton and algae and things like that, that accumulated on the ocean floor approximately 300 million years ago. So when these organisms died, they were living in the ocean and they died, their remains settled at the bottom of the ocean floor, where they became covered in sand and silt and other sediments. And then over the next several 100 million years, these remains were buried under all this sediment, and they were subject to very high pressures from the weight of the water itself from the ocean, as well as the overlying sediments. And then as they got pushed deeper underground, they were also exposed to the geothermal heat from within the earth. And as these remains were exposed to higher temperatures and very, very high pressures over the course of hundreds of millions of years, they were transformed into natural gas. And as I mentioned before, natural gas forms under similar conditions to that of crude oil, but it's typically associated with being exposed to higher temperatures that break up these hydrocarbon molecules into smaller gaseous molecules. If you remember back to the crude oil lecture, diesel was this very long carbon chain with hydrogen on it, whereas if we look above here, we can see that there are these smaller molecules of a singular carbon atom surrounded by hydrogen. Okay, and then once formed, natural gas accumulates in these underground reservoirs, either alongside crude oil deposits, or they're trapped within porous rock formations deep underground. And similar to coal and crude oil, natural gas is considered to be a fossil fuel and a non-renewable resource because it is made from the fossilized remains of plants and microorganisms over the course of hundreds of millions of years. Okay, now let's go on to the next section. How natural gas is extracted. So natural gas is extracted from underground reservoirs through a process called fracking, or hydraulic fracturing. We also covered this, we covered a bit about fracking in the crude oil lecture, but I'll go into a little bit more detail here. So in the fracking process, a well is drilled. I'll use my green highlighter. A well is drilled to go directly underground, and then once it reaches the rock that contains the natural gas, it then starts drilling sideways. And then once a well has been drilled, there's this installation of steel and cement casing here along the sides of the well. And the purpose of this is to keep the gas and fluids inside the well so that they don't end up getting into this not as solidly packed rock, soil, and dirt up above here. And then after this well has been drilled, there are small holes that are created in the well through high pressure through high pressure liquid, sand and rocks that are sent, and chemicals that are sent down here. And then once these, there have been these little holes that are present on the side of the well, there is a fracturing fluid, which again is a mixture of water, sand, and chemicals that's pumped at a very, very high pressure down into the well that leads to the cracks in the rock here. And when the rock down here gets cracked, this allows a pathway for the trapped natural gas to flow into the well, where it is collected and then brought to the surface, where it is collected and then put into pipelines for consumption. All right, on to the next section. All right, so how does natural gas, combusting natural gas, produce energy? So natural gas undergoes a similar combustion process to coal and crude oil products. So here you can see that the primary reactants in this chemical reaction, there is the methane, and then there is the oxygen, and when these two react with each other, the primary results are thermal energy, which is what we want for the power plant, carbon dioxide, and water. But because natural gas is not composed of just purely methane, there are some other impurities that are present. And then the air that's brought in for the reaction has nitrogen, and hydrogen sulfide is a common impurity in natural gas. And so as a result, additional chemical reactions occur during this combustion process that produce some of the pollutants such as nitrogen dioxide and sulfur dioxide. One thing to note here is that natural gas produces significantly fewer air pollutants than coal. Typically, if you compare the output, there's about a 50% reduction in greenhouse gases and more than a 90% reduction in air pollutants when switching from coal to natural gas. So there are some significant benefits there. And as mentioned in the previous lecture, I'm just going to repeat this again. In the combustion process, we are taking the chemical energy, which is contained in the bonds between the atoms within the methane molecules. And during this reaction, that energy is released in the form of thermal energy. And then it's the power plants that take that thermal energy and convert it into electricity, which is what we will be covering next. All right. So here we go. So how is natural gas used to generate electricity? So there are three main types of natural gas power plants. There is a simple cycle power plant, a combined cycle, and a cogeneration. And I'm going to briefly go through how all three of these power plants work. So the first one is the simple cycle. And simple cycle power plants are very similar to the combustion turbines that are used to generate electricity from naphtha and kerosene, which are crude oil products. Now, I'm going to be introducing this new term called efficiency. And here the efficiency of a simple cycle plant is labeled as 30 to 45%. And what efficiency is, it's the percentage of the fuel's energy that is successfully converted to electricity. So in the process of combusting a fossil fuel, some of the energy from the fuel is lost to heat that is released into the atmosphere. And in the case of natural gas power plants, different power plants have different levels of efficiency. But the reason why I'm only discussing efficiency now, and I haven't discussed it in the previous coal and crude oil lectures, is because the choice of which type of natural gas power plant to build out is primarily dependent on the efficiency of the power plant and the ramp rate, which is just how quickly can the power plant respond, or how quickly can the power plant, how can I put this, change its power output. So here we look at efficiency. Oh, no, didn't mean to erase that. We look at efficiency here of a simple cycle power plant. It's at 30 to 45% efficient. So that means 30 to 45% of the energy released in the combustion reaction of the natural gas is converted to electricity. And so here, let's quickly run through this. So there is air. There's an air intake in this power plant. The air is then compressed. Then here, natural gas is injected into the hot and high pressure gas. Oops, injected. And then what happens is that it combusts. And what happens here is that these very hot and very high pressure gases are pushed in the direction of a gas turbine. So here is a gas turbine. Here's the gas turbine. And these gases, the exhaust from this combustion reaction, are sent through this turbine. This turbine spins and converts the thermal energy of the combustion reaction into rotational kinetic energy, and then that is connected to a generator, and that generator converts the rotational kinetic energy into electricity. That electricity is then transported with power lines to the electric grid. Electric grid, where that electricity is then distributed to homes and businesses, etc. And then here, the primary products, or the exhaust gases of that combustion reaction, are released. So I'll just say exhaust gases. So this is how a simple cycle power plant works. Okay, the next type of power plant is a combined cycle power plant. So here we go. It's a little bit more complicated. So combined cycle systems are like a combination of a simple cycle power plant and a coal-fired power plant. They use both gas turbines and steam turbines. So first, here, same similar process. So there's air intake. Intake. It is compressed. There is natural gas injected here. There is the combustion reaction that happens here. The hot gases from the combustion reaction are directed towards a gas turbine. Directed towards a gas turbine here, which is connected to a generator, which converts that rotational kinetic energy into electrical energy. But instead of just releasing the exhaust gases from here, what happens is that these exhaust gases are then funneled to heat up water to turn it into steam. And so right here, these exhaust gases that have gone through the gas turbine here are usually very hot. They're typically 500 to 650 degrees Celsius, or 930 to 1,200 degrees Fahrenheit. And so this is still very hot, still very much has the capability to heat water and turn it to steam. And that steam, or when water turns to steam, it takes up a much larger volume. It's under high pressure, and that steam is sent towards a steam turbine. This is similar to a coal-fired power plant, and as the steam goes through that steam turbine, that creates rotational kinetic energy, which is then connected to a generator, which then generates electricity, and then finally those exhaust gases are released. Now this is there's another set of steps on top of the simple cycle power plant, and the benefit here really comes with the efficiency. So the simple cycle power plants, let me see, what were the numbers here? 30 to 45% efficient, whereas with a combined cycle power plant, they're typically 45 to 65% efficient. So this means combined cycle power plants can generate more electricity with the same amount of fuel as a simple cycle power plant. Now, where the disadvantage mainly comes here is the ramp time. So up here, the simple cycle plants, they're able to change their power output in approximately 5 to 30 minutes, whereas a combined cycle power plant typically takes 30 minutes to 4 hours to change its output. So those are some of the trade-offs. Now the third type is the cogeneration plant. So if we move down here, there is the cogeneration plant. And the cogeneration plant functions very similarly to a combined cycle power plant, but instead of using those exhaust gases to heat water, to turn it into steam, to spin a turbine, this heated water is instead used for some industrial process, and it could be used for food processing, like for example pasteurization needs heat. It could be used for chemical manufacturing, it could be used for building space heating, etc. So here you can see I've drawn this cycle going through a building right over here. And one of the examples is on UC Berkeley's campus, one of the universities in California. They have a cogeneration plant that is located on campus that takes natural gas and generates electricity for the campus, but then the steam that is produced from this natural gas power plant is then used to heat the buildings on campus. So that's pretty cool. And one of the benefits of cogeneration is that it's very efficient, 75 to 85% efficient. And this is taking into account that it first uses this combustion reaction to generate electricity, and then this heat is transferred through buildings and for industrial processes. Now the ramp time is pretty similar to the combined cycle power plants, which is 30 minutes to 4 hours plus, but typically it is constrained by the heat load, this building being the heat load. So just because you want to produce more energy or more electricity here, you don't necessarily want to ramp up your cogeneration plant and then cook the buildings. So typically the heat load is what determines how much natural gas is being used in the system rather than the amount of electricity that they are desiring to generate. And the one other thing is cogeneration plants are sometimes referred to as combined heat and power, or CHP. So be on the lookout for those terms as well. So those are the three types of natural gas power plant. Now in the next section, we're going to go over some of the characteristics of natural gas power plants. So let's start by describing their controllability. So Natural gas power plants, as you've probably been able to pick up, they are dispatchable resources. So they can be, operators are able to control how much electricity they are generating at any given point. Now, simple cycle plants, to change their output typically takes 5 to 30 minutes. And they are about 30 to 45% efficient. Combined cycle plants take about 30 minutes to 4 hours to change their power output, and they are about 45 to 65% efficient. And then finally, there are the cogeneration plants, which take 30 minutes to 4 hours plus, but they are typically constrained by the heat load. The heat load is determining how much electricity it's going to be generating as a byproduct, and they tend to be 75 to 85% efficient as an approximation. Okay, now for the fuel supply chain. The fuel supply chain is a bit complicated for natural gas systems. So we start with the fracking site here. And from the fracking site, it is typically transported by a pipeline to a processing plant, which takes out some of the pollutants, such as hydrogen sulfide, that is located, or that is usually in that raw natural gas that is extracted at the fracking site. And then from the processing plant, it is then sent into a pipeline where it can go two directions. One, it can be stored in large storage containers, and then when there is a desire to use it, it can then be added to pipelines and then sent through pipeline to natural gas power plants. Now, if there is a desire to ship this natural there very long distances, such as across the water to another country. There is an extra step in this process. So with coal and with crude oil, they can just be put into containers. So coal can just be put into a normal shipping container. There's no stress around that. Crude oil products can just be put in barrels. But natural gas, it is a gas. So it's, from a volumetric standpoint, it doesn't contain very much energy per unit volume. But when you're shipping something on a ship, volume really matters here. So before it is shipped out, it typically goes through, didn't mean to erase, I meant to circle. It goes through a process called liquefaction. And in the liquefaction process, it is the process of cooling down the natural gas to negative 162 degrees Celsius or negative 260 degrees Fahrenheit. And this causes the natural gas to condense into a liquid, commonly known as liquefied natural gas. And you'll sometimes see LNG. Those acronyms mean liquefied natural gas. And so it is condensed down into a liquid form, which reduces its volume by a factor of about 600. So it's much more economical to transport natural gas in LNG or liquefied natural gas tanks than in its gaseous form. So once it has gone through the liquefaction process, it can be transported by a truck to a port. And so, for example, the United States produces a lot of natural gas, and the United States ships natural gas to, for example, Europe. And so this process could be going on in Texas, and one of the southern states in the United States that produces a significant amount of natural gas. It could be sent off from a port in the southern United States, put on a ship, arrive at a port in Europe, maybe Portugal or Spain, for example, And then from there, it can be trucked to a gasification plant where they take the liquefied natural gas, they warm it back up so that it is back into its gaseous state. And then from there, it can be transported by pipeline to storage tanks, and then from storage tanks through pipelines to the natural gas power plants. So that's the fuel supply chain. The simplified natural gas fuel supply chain. Now, for fuel storage, so natural gas power plants have limited on-site storage. So unlike coal and crude oil products, natural gas is quite difficult and expensive to store because it has to remain under very high pressures and kept at a very low temperature in order to store it economically in liquid form. And because of these storage challenges, most natural gas power plants maintain a small or don't maintain at all an on-site fuel reserve, and instead rely on the continuous supply of natural gas delivered through pipelines. And because of this reliance on a continuous fuel delivery, this means that natural gas power plants are vulnerable to short-term supply chain disruptions. So let's say something happens with a pipeline, maybe a pipeline has a leak, or for some reason the operators have to shut down the pipeline. This could immediately cut off natural gas access to a natural gas power plant, and in that case, it would have to shut down. So it is vulnerable to short-term supply chain disruptions. Okay, let's look at the capital costs of building out these different types of power plants. So these numbers are in US dollars in 2023. So a simple cycle power plant is the cheapest to build out per megawatt hour. It's typically about $750,000 per megawatt, or not per megawatt hour, per megawatt. And the typical size of simple cycle power plants is about 200 megawatts. So this means that the cost to build out a power plant is about $120 million on average. Now the combined cycle plants, a little bit more expensive because there's that extra build out that is added on for the steam turbine at the end. So it's about $1 million per megawatt. And combined cycle plants tend to be quite a bit bigger than simple cycle at around 750 megawatts. And so this means that the typical cost for building out a combined cycle power plant is roughly $750 million. Now, a cogeneration plant, they are typically built out at industrial facilities, and they are dictated by the amount of steam or heat that is needed for the industrial process. So they tend to be smaller than simple cycle and combined cycle power plants at about 50 megawatts. But because of the expensive, it's quite expensive to have to either retrofit or design these industrial buildings to be able to use that steam from the cogeneration plant. So they tend to be quite a bit more expensive at about $2 million per megawatt. And so this means that the average cost of a cogeneration plant is about $100 million in the United States. Now, in certain regions around the world, it might be a little cheaper, it might be a little more expensive, but this is the data that I had access to just for this example. Okay, so let's go into the operational costs. So before I dive into the numbers, the operating costs of natural gas power plants depends largely on the price and the availability of natural gas. Countries that have abundant domestic natural gas resources like the United States or like Russia typically have lower fuel costs than countries that rely on imports, such as a lot of the European countries, South Korea, and Japan. So these numbers here that I have written are based on US prices, which produces a lot of its own natural gas supply. So these numbers are going to be most likely cheaper than in other regions around the world. And so here in the U.S., in U.S. dollars in 2026, the operational costs, which includes fuel, it includes paying operators and maintenance, is roughly about $45 per megawatt hour. So it is significantly cheaper than producing electricity with crude oil products. Combined cycle is at about $28 per megawatt hour, so much cheaper. And then cogeneration plants are at about $25 per megawatt hour. And here you've seen I have added a note that says effective. This takes into account that some of the fuel is being used not just to generate electricity, but also to provide heat to a service. So if we look at the effective cost of electricity, taking into account that some of the cost of this plant is for the heat, the effective cost is about $25 per megawatt hour. Okay, so that's the rough operational costs. Now, air pollution and greenhouse gas emissions. So, natural gas has similar air pollutants to crude oil products and to coal. But one of the things to note here is that in comparison to coal, natural gas typically has, or using natural gas over coal results in about a 90% reduction in air pollutants in comparison to coal-fired power plants, even if they have some sort of pollution control that takes out some of the air pollutants that are generated from coal combustion. And then when using natural gas, there is approximately a 50% reduction in greenhouse gas emissions in comparison to coal. But there is one important note here. These numbers are at the power plant level. But one of the big problems with natural gas systems is that there are methane leaks along the pipelines. And so methane here is a greenhouse gas, and natural gas is methane. And methane is quite a potent greenhouse gas, and so if pipelines are not maintained properly, there can actually be a significant methane leakage along the pipeline delivery to the natural gas power plant. So these numbers here are just at the power plant level, but if we look at the full natural gas supply chain, if those pipelines are not well maintained, they can actually have very significant greenhouse gas emissions. From the overall natural gas standpoint, or the overall supply chain standpoint, not just the power plant itself. Okay, role on the electric grid. So here, each of the different types of natural gas power plant actually play a different role on the electric grid. So simple cycle power plants, we mentioned they can change their power output quite quickly. And because they can change their power output in a matter of minutes, this makes them well suited as peaker plants. So they're able to respond to sudden increases or decreases in electricity demand. And so here you can see I've labeled it, didn't mean to erase that. I've labeled it as a peaker plant. And then combined cycle plants, since they take a little bit longer to respond in comparison to simple cycle plants, they are typically operated as intermediate plants, or actually they're also operated as baseload sometimes. And so this term, an intermediate power plant, is a new term. And what an intermediate power plant is, it is a dispatchable resource that can adjust its power output in around an hour, so it responds to gradual and predictable changes in electricity demand. And then finally, cogeneration, because is operated as a baseload resource, and this is because cogeneration is primarily the primary purpose of it is typically to provide heat, and generating electricity is more of a side part of it. So it's just operated continuously throughout the day in most instances. Now, if we look at this chart here, the x-axis represents the time of day, and the y-axis represents the electricity either being demanded or generated in megawatts. And so, like I've shown in the previous lectures, this blue line here that I'm highlighting with my green highlighter, this is supposed to represent how much electricity is being demanded throughout the day. So in the evenings, there tends to be less electricity demand because people are sleeping, they have their electronics turned off, they have the lights turned off. But then in the middle of the day and in the later afternoon, there tends to be higher electricity being demanded because people are turning on their lights, they're turning on their TVs, their coffee makers, they're charging their cars, etc. So there tends to be higher amounts of electricity demanded during these times. So if we look at an example of how these power plants operate, similarly to coal, cogeneration is just going to be operated consistently throughout the day. The combined cycle power plant will typically operate, it could operate throughout the entire day as a base load as well, but in this example I've illustrated it as an intermediate load where it operates roughly between 5 a.m. and then maybe this is like 10 p.m. For example. So it has this little ramp up period here, then it operates consistently throughout the day and has a little ramp down period in the afternoon. And then finally, simple cycle plants, because they can respond pretty quickly, but they're the most expensive out of the 3 natural gas power plants. They will respond to just this uptick in electricity demand in the afternoon and maybe only operate over the course of 3 or 4 hours, if not less. Okay, so that's it for the characteristics of natural gas power plants. Now I'm going to start discussing the geopolitical considerations of using natural gas. So one concern with using natural gas is that, similar to crude oil, the production of natural gas is highly concentrated in a relatively small number of countries. So here, if we look at this map, we can see the United States is producing the most natural gas out of any country in the world. And then Russia comes in at second here. And then we have a handful of other countries such as Iran, China, Canada, Qatar, Australia, Norway, Saudi Arabia, and Algeria that also produce a significant amount of natural gas. But if you are pretty much any other country in the world, this is a pretty concentrated supply chain of natural gas across 10 countries here. And similarly to how I discussed with crude oil, this leads to what we call as energy dependence. So as a result, the countries that rely on rely heavily on imported natural gas, such as many of the European countries, Japan and South Korea are just some examples, they become dependent on the stability of these international suppliers. So any geopolitical conflicts, trade disputes, export restrictions, or disruptions to pipeline infrastructure significantly affect the fuel availability and the prices of natural gas, which can be generally a security concern for countries. And one example of this was in 2022 when Russia invaded Ukraine. Europe was heavily importing natural gas from Russia, but then many of the European countries cut off natural gas imports from Russia, which caused prices to skyrocket in Europe. Now, they replaced part of that demand from the US and from Canada, as well as a number of other countries. But by cutting off Russia, a singular country, this led to a dramatic increase in prices there. Okay. The next geopolitical consideration, fewer emissions, yet typically higher costs. So compared to coal, natural gas produces significantly lower emissions, both from air pollutants and greenhouse gases. However, these environmental benefits often come with higher fuel transportation costs, higher storage costs, higher infrastructure costs for countries that don't produce their own natural gas. And so what happens is that if a country is not one of these 10 that's able to produce a significant amount on their own, utilizing natural gas over coal can typically be more expensive. All right, and then the last point that I've covered with all of the fossil fuels is the disproportionate impacts of climate change. So although natural gas produces fewer greenhouse gas emissions than coal when methane leaks are minimized, it is still a source of greenhouse gas emissions. And regions like Europe and North America and the Middle East are regions that burn a lot of natural gas, and so they are major contributors of greenhouse gas emissions through their natural gas use. But these regions are projected to be less impacted by climate change in comparison to sub-Saharan Africa, Southeast Asia, and island nations, which use relatively much less natural gas and contribute much less to global greenhouse gas emissions than these major regions. Okay, that is it for our natural gas lecture. Let's see, yeah, that's pretty much it for this lecture. Thank you so much for watching. This is the very first version of our natural gas lecture, and we know that there is much to improve here, so we would love your feedback. Is there something that you think wasn't explained clearly enough? Do you think that there is other information that we should add? If so, we're going to be adding a link to a feedback form in the video notes. You can also visit our website to fill out this form. Then once we have received a sufficient amount of feedback, we will update the lecture, we will re-record, and we will post the updated video. So for those of you who will be providing feedback, thank you so much for helping to improve the quality of publicly available education. And also, if you found this lecture valuable, please consider donating. This will help us continue to make publicly available educational content on the electricity industry. You can do this by visiting our website at pearlstreetstudio.org, or we will also include a link in the notes for donations. All right, that's it for now, and see you at our next lecture on geothermal energy.